All right, what is a confidence interval? So this ugly equation here looks kind of nasty. Is hopefully what I'm going to describe to you. Because that is the formula for confidence interval. Now, some things you need to understand. First off is again, thanks to Krista Floor, I think I pronounced that correctly, for this graphic. It's beautiful. But this is our normal distribution with our mean and our standard, one standard deviation, you have 34% of your data occurs there. If you go out two standard deviations, you have another 13.6% on this side. So this side has approximately 64% or 68%. I can't add, sorry. This is approximately 95%. Whoa, keep moving that. 95%. And if you go out three standard deviations, which is way out here and out here, you're looking at 99 point so many degrees. So 99.7. I guess there it is. It's all on the bottom. 68.2, 95.4, and 99.7 percent of your data if it's normally distributed. So let's say, the first thing we have is a point estimate. That's generally the first thing you find when you have a set of data. So I have a problem here. You're a ball bearing manufacturer and you need to find out with 95% confidence the mean of the entire population of ball bearings you produced at your factory that day. So you, and I see it doesn't fit, so you randomly selected the 100 ball bearings below and measured them all. What you find is that the mean of this sample is 2.54 centimeters with a standard deviation of 0.3 centimeters. So here are your ball bearings, just in case you're wondering what a ball bearing looks like. There's the 100 you sampled. And you pulled them out of this big vat of an entire population of ball bearings. This 2.54 is a point estimate. You used 1 point to estimate it. So in our case, the point estimate is 2.54, which is our sample mean, X bar. An interval estimate is what we're going to use to estimate the entire population. So we're going to find some interval, and here's the confidence interval. So now we're going to use this to go ahead and see what with 95% confidence, what the interval would be for the actual mean. So first off, we know our X bar. X bar is the sample mean. Sigma is our sample standard deviation, and I used the wrong symbol. I apologize. That should be S. And then N is how many we sampled in the whole equation. This is our z-score from our normal curve. So far we could plug it in so it looks like this. So 2.54 minus z sub alpha, wow, I can't draw an alpha, sub alpha divided by 2 times your standard deviation. Well, from our problem, our standard deviation was 0.3. Oops. And so 0.3, let me extend the page here. So 0.3 over the square root of 100, because we sampled 100 ball bearings, is going to be less than the mean, and it's also going to be less than X bar, again, 2.54, plus your Z alpha divided by 2, so your Z-score of sigma, well, we know sigma, our standard deviation, sorry, S, of 0.3 divided by the square root of 100. So we just need to concentrate now on this part. Okay, the Z alpha divided by 2. Well, I'm going to show you two ways to calculate that. One electronically and one with just a table out of the back. So with a 95% confidence interval, so let's say here it is. So somewhere out here, We don't know where for sure, but we'll find it. So this is, let's say, 95% confidence. All the data in here. Somewhere our mean is going to lie in this region between these 2 points. And to find out this z-score exactly, I just kind of guessed because I knew 2 standard deviations was slightly more than 95%. So it's got to be in that region somewhere based on the empirical rule. If you go back and look at that, so we know it's somewhere in this region because of the 95.4%. So to find out exactly what you do is we're going to use this z-table first, and I have a picture of it. And what this z-table does, if you look down here on the bottom, is this tells you the area. If the area of the whole thing, if you shaded in the whole thing, it'd be 1. The area is 1. The area for each z-score from the mean to the z-score we're talking about is what this table gives you. So in our case, we want a 95% confidence interval. And so, okay, so it is, we want a 95% confidence interval, which is really from here. I'll stick that, running a little slow here. So that's really from here to here for 95%. Well, this table only gives half of that. So we'll divide that by 2, which is 47.5%, which would be 0.475 in this table. And so we'll go find that number in here. So 0.475. 0.475, here's 0.4738. Oh, there it is. So there's 0.475. So that corresponds to 0.06 here and 1.9 here. So we know our z-score for 95% confidence interval is plus or minus 1.96. So that's the number we're going to use in our formula. I think I was at the bottom of this page. Yep, there it is. So now we know that to find our confidence interval, it's 1.96, 0.3 divided by 10, because that's the square root of 100, is less than mu is less than 2.54 plus 1.96 times 0.3 divided by 10. And so you get out your calculator, you do all the calculations, and you get 2.4812 is less than mu is less than 2.5988, you know, plugging all that in. And so we know that our mean is, for all of our ball bearings, we're 95% confident that the mean of our ball bearings that our factory's spitting out is between 2.48 and 2.60. So somewhere between there, we're 95% sure that our mean is for the whole population, not just the 100 that we did. We know that. But for all the ball bearings that whole factories produced that day, we know the mean is in between 2.48 and 2.6. And I also wanted to show you another way. If you go online, sorry, I just flopped around on you because I made a mistake when I did this. But I also was going to show you how to find this z-score or this confidence interval with an online calculator. This one's pretty cool. I just Googled z-score calculator, and this is what I came up with. So Claremont Graduate University WISE PZ calculator. So I've already entered kind of what I'm looking for. This 0.025, whatever. You really don't need it. You can just hit the graphic to kind of help you. I think visual is a lot better. And so this is a one-tail z-score. So if we're looking for the blue area or the red area, but we're really looking for the blue area in this 95% confidence interval. And I've already got it set. There's 0.95, 0.950 there for P middle. and p-tail is a 0.05 that's left over, and it shows you your raw score, your z-score plus or minus 1.96. But what's cool about this is you wouldn't have to do 95% confidence. You could do, maybe you want 99% confidence. So let's drag that thing to 0.99. Oh, there it was. So if you wanted to do a 99% confidence interval, you'd use 2.582 for your z-score and your confidence interval. So you give up a little bit in accuracy, but then you're 99% confident that's where your mean is going to be located using that value. Or maybe you don't even need anything that accurate. Maybe it's around 90%. So 90% would be about 1.65. So this is kind of a neat little neat one just to do. You know, if you go to 64% confidence, you know, there's a z-score of 0.923. So that's kind of a nice little calculator. I'm pretty impressed with it. So good luck on this. I hope this helped you. You can also use your graphing calculators, but I like to just use tables and then go online and look instead of spending lots of money on giving TI a whole bunch of money that you don't need to give them if you already have a computer. So best of luck. See you next time. Thanks for watching.